In this session, we'll be looking at various evaluation parameters. We will begin with some techniques of using sample data for training and testing. We will then move ahead to prediction of performance. Then we will be looking at test to measure data mining methods, followed by the role of cost in data mining techniques. Then we'll look at few visualization charts like lift charts and ROC curves. In the end, we'll be looking at minimum description length principle. So let's begin. Training and testing. So we measure the success of a classification procedure by using error rates. Measuring success rates using training set is highly optimistic, as we have already used this training set to train our model. So using this training set again to measure the error rate will be highly optimistic. If we use the training set to measure our error, then this kind of error is called resubstitution error. So in practical cases, we have a separate test set for calculating success error. Now test set should be independent of the training set. There should be no dependence of the test set and training set. Also, sometime to improve our classification technique, like suppose we want to do pruning of our classification technique, we have a separate test called validation test. So basically we work with three sets. We use training set for the training purposes, then we use validation set to improve our techniques, and then in the end to calculate our error if we use the test set. When we hold out some part of the training set for testing, which won't be used for training now, this process is called holdout procedure. Now we come to predicting performance. Now success rate equals to 100 minus error rate, and though the success rate which we get is expected success rate, we want the true success rate. How do we calculate our true success rate if we have our expected success rate? Expected success rate is simple. It's basically the number of successes out of a total of n instances for a learning model. But if we approach towards large value of n, then f, that is the expected success rate, follows the normal distribution. Therefore, we can use the properties of normal distribution to get our true success rate from our expected success rate. We represent our true success rate as p, and we basically want a confidence percentage. For a particular confidence percentage, we want our true success rate range. For example, say our f, that is the expected success rate, is 75%, then p will lie in this range 73.2 to 76.7 with 80% confidence. So basically what the parameters that will be given to us are f and the R confidence range, and from that we need P, that is the true success rate. Now using the properties of statistics, which we are not going to explain over here in details, the mean of f, we told you that f follows a normal distribution and the mean of f is P, that is the true success rate, and the variance of f is P into 1 minus P divided by n. So if we want to use the normal distribution data, we will have to make the mean of f equal to 0 and the standard deviation equal to 1. So suppose now that our confidence percentage is given to us and it's C. Now a normal distribution graph is basically a two-tailed graph, so we'll be using its two-tailed property to get the appropriate range of P. Also, the entire area under the normal distribution curve, if we represent it by 100%, so basically if our confidence is C, therefore we will have to leave 100 minus C percent area of the normal distribution, and we'll be using this to get our value of P. So after applying all our manipulations, which we are not going to explain over here in details, we get the following value of P. As you can see, the plus minus basically in the expression of P will give us two values of P, which will represent the endpoint of the range of P. That is the true success rate, and this is how we get a true success rate given an expected success rate and a confidence percentage. Now we come to cross validation. We use cross validation when the amount of data is small and we need to have independent training and test set. As we already told you that we need to have independence between these two set to get a more correct, more appropriate error rate. Now it is important that each class is represented in its actual proportion in the training and the test set, and this property is called stratification. One of the most important cross-validation technique that we use is stratified tenfold cross-validation. What we do in stratified tenfold cross-validation, we basically divide our data into 10 folds, into 10 equal parts, and we basically take one part, one fold, turn by turn, use it as our test set, and the rest of the 9 parts are used for training. And therefore in the end we have 10 results, and we basically do an average of those 10 iterations. The only problem with this stratified tenfold cross validation is that it's computationally intensive, since to get a single result we are going to do 10 iterations of our learning method. What are the other estimates? The other estimate is leave one out, where one instance is left for testing and the rest are used for training. This is iterated for all instances and the error are averaged. The advantage of this is basically we are going to use larger training sets. Rather than using just 9 by 10th of the data for training, here we are using all the instances minus 1 for our training. The disadvantage again is that it is also computationally intensive and it cannot be stratified. Why it cannot be stratified? Because the only instance that we'll be using for error, we cannot do stratification if we have only one instance. The next technique we are going to study is 0.632 bootstrap. So what do we do in bootstrap? Till now what we are doing, that we were not reusing the data which we have. So in bootstrap we basically reuse the data. What do we mean by reuse? The data of n samples is sampled n time with replacement. So by replacement we are going to do reuse of data to give another data set with n instances. Now there will be some repeated instances in the second set, and here we define the error rate as using this formula. So error in test instances plus some factor into error in training instances. Error in training instances is also known as resubstitution error, which we studied earlier. Moving ahead, now we come to methods to compare two or more data mining algorithms. Till now we were dealing with the success rate, with the error rate of a single algorithm. Now we will be comparing two or more data mining algorithm. We cannot directly use error rate for this purpose, as the error rate might have been calculated on different data sets, and therefore it is not a very credible factor to compare two machine learning algorithm or data mining algorithm which have been tested on different data sets. So to compare algorithm we need some statistical test, and the statistical test that we will be using is students t-test. This test helps us to figure out if the mean error of the two algorithms are different or not for a given confidence level. So we'll be using pair t-test, which is a slight modification of our standard students t-test. Now these are the steps of pair t-test. We initially suppose that we have unlimited data, and now we repeat the following steps. We find k data sets from the unlimited data we have. Then we use cross validation with each technique to get the respective outcomes. So what do? The k data set which we have, we take each data set and use cross validation technique on it, and then we run each and every algorithm on that data set, and we get the respective error. Say we have two algorithms, so we get, for the first data set we get the error x1 and y1, and similarly we get the error x1 till xk and y1 till yk. Now if we represent mx as a mean of x values and similarly my, then di is defined as xi minus yi. So basically di is the difference of corresponding errors, and now t statistic is defined as d mean upon the variance, which we define over here as square root of sigma square d divided by k, where k is the number of instances and sigma d is basically the standard deviation of d. Now, based on the value of k, we get a degree of freedom, which enable us to figure out a z for a particular confidence value. So we use a table. The table will depend on our degree of freedom, which in turn depends on the value of k, and based on the value from the table, we can conclude whether the two algorithms are different or not. In case the value in table is equal to 0 and we get the value of t equal to 0, then we can say that this is null hypothesis and they don't differ. Otherwise, the two means differ significantly, and hence the two data mining algorithms are not equal. Now we come to predicting probabilities. Till now we were considering a scheme which, when applied, results in either a correct or an incorrect prediction. That is a 0-1 loss function. Either we have a correct answer or we have a wrong answer. Now we will deal with the success in case of algorithm that outputs probability distribution. Now we are not getting a definite answer in the form of correct or incorrect, but we are getting a probability distribution, like what we saw in the case of naive Bayes. Now, how do we compare the success of such methods which output probabilities? One of the technique which we use is quadratic loss function. Now, in quadratic loss function, for a single instance, there are k outcomes of or classes. This is an assumption that we have k outcomes or classes for a single instance. Now using our learning method, we have the probability vector for this instance as p1 till pk. So p1 is basically the probability that the instance belongs to the class 1. P2 is the probability that instance belongs to class 2, and similarly pk is the probability that instance belongs to class k. The actual outcome vector is a1 to ak, where a1 will be 1 if it is actually the class, or if it will the rest of them will be 0. So whatever is the actual outcome will be 1, the rest of the values in the set a1 to ak will be 0. Now we have to minimize the quadratic loss function, which is given by summation of pj minus aj. So basically here we are representing the quadratic loss function for a single instance. The value of j here will vary from 1 to k. The minimum, if we analyze this function, then we come to the conclusion that the minimum will be achieved when the probability vector is the true probability vector, and not the one which is uh, which we have got as a result of our machine learning algorithm, but rather it's the true probability vector. The next method to rate the success of uh, algorithm which output probability distribution and not a definite answer is informational loss function. Informational loss function is given by minus log of pi, where pi is the probability of the class which is the actual outcome. Now again we reach the minimum at true probabilities. We come to the differences between quadratic loss function and informational loss function. While quadratic loss function takes all the probability under consideration, informational loss is based only on the class probability, that is the class which has been predicted. Now, if you look over here in the expression, we only have pi and no other probability is there in the expression. If we go to the previous slide and look at the expression for quadratic loss function, here you can see that irrespective of the outcome, we are using all the probabilities in our expression, and hence quadratic loss function depends on all the probabilities. The second difference is, while quadratic loss function is bounded as its maximum output can be 2, informational loss function is unbounded as it can output values up to infinity. Now we come to counting the cost. Now we just talked about what a algorithm can have different outcomes and it can have different type of error, but each outcome might have different cost as well. For example, if we talk of a loan decision, the cost of lending to a defaulter is far greater than the lost business cost of refusing a loan to a non-defaulter. So this is one of the example where cost plays a crucial role, and therefore it makes sense to include the cost in either the training part or in the testing part. Now suppose we have a two class prediction. The outcome can be of the following form. Here the rows represent the actual class and the column represents the predicted class. If our actual class and predicted class are the same, then we have true, positive and negative respectively. Otherwise we have false negative and false positive. Now true positive rate is defined as true positive upon true positive plus false negative, and similarly we have the false negative rate. Overall success rate is given by number of correct classification, that is TP plus TN upon total number of classification. Error rate is again given by 1 minus success rate if the success rate is given in a fraction. Otherwise we'll have it 100 minus success rate if the success rate is given in the form of a percentage. In multi-class case, we also have a confusion matrix like this. If you see the left part of this diagram, this is a confusion matrix where the three classes that can be there in the outcome is A, B, C, and these represents the actual classes and these represents the predicted classes. When again for a case where both actual class and predicted class are the same, are a correct classification. Now the left part is an actual instance, actual machine learning algorithms output, and this right part is basically a random output. The diagonal represents the successful cases. In the diagonal we have predicted class equals to actual class. Now we come to kappa statistic. Kappa statistic is equal to D observed minus D actual upon D perfect minus D actual. D here represents the number of attributes, number of integers in the diagonal. So if we talk of D observed in the previous case, so D observed will be 88 plus 40 plus 12, that is 140, and D actual is 82. D perfect minus D actual. D perfect will be basically if we consider all the instances have been classified accurately, and using this formula we get our kappa statistic. Kappa is used to measure the agreement between predicted and observed categorization of a data while correcting for agreement that occur by chance. It does not take cost into consideration. So till now we haven't take cost into consideration. Now we come to classification with cost. So now we are going to include cost while we are doing classification. So below you can see an example cost metric, though this particular cost matrices will just give us a number of errors. As you can see, if the prediction is right, then the value is 0, otherwise it's 1. Now success rate is measured by the average cost per prediction, and we try to minimize the cost. Now, expected cost equals to dot product of vectors of class probabilities and appropriate column in cost matrix. So for example, if we have our class probability vector, say we have PA, PB, PC as our class vector, and we would like to if we multiply that by this particular column, then we'll have our one value of our cost. And similarly, if we multiply by this, we have a different cost, and if we multiply by this, we have different costs. So basically that shows that if we actually predict A, then we'll have different cost, and predicting B and C will give us different cost. Now, steps to take cost into consideration while testing. First, use a learning method to get the probability vector. For example, we can use naive Bayes. Now multiply the probability vector to each column of a cost matrix one by one so as to get the cost for each class or column. Now select the class with the minimum cost, or maybe maximum, depends upon how do you define your cost matrix. Now we come to cost sensitive learning. In the previous instances we basically took cost under consideration while testing. Now we will include cost while we are learning. To do this, we can modify our training set. How can we modify our training set? We can change the ratio of instances in the training set so as to take care of the cost. For example, we can do replication of an instance of a particular class so that our learning method will give us a model with less errors of that class. Since the number of instances belonging to this particular classes are more, so our learning model will adapt and uh, will basically give a higher priority, give a lesser error on this particular class, and this is how we can incorporate cost in the learning stage. Now we come to some of the visualization technique. The first one that we'll be dealing is lift chart. In practice, costs are rarely known. In marketing terminology, the response rate is referred to as the lift factor. So we can compare probable scenarios to make decision. A lift chart allows visual comparison. For example, suppose we want to send some promotional mails out to say 1 million households, and if we mail to all, then only 0.1%, that is 1000, we get only 1000 responses. So using some data mining tools, we identify a subset of 100,000 household of which 0.4% respond, that is 400. So what we have a lift of 4, that is 0.4 upon 0.1, so we have a lift of 4. So again, the lift factor basically represents the increase in the response rate. Steps to calculate the lift factor: we decide a sample size. Now we arrange our data in decreasing order of the predicted probability of a class. What class to take as a factor while arranging our data? The class which we will base our lift factor on, positive or the positive class. For example, in the previous case, uh, say we represent yes as an yes for an instance which sends us a reply, and no for an instance which does not send us a reply. So in that case, we'll basically arrange our classes based on the instance is where the classification is yes, or on the yes probability. Now we calculate sample success proportion equals to number of positive instances upon total sample size. Now lift factor is given by sample success proportion, the one which we calculated in the previous step, and the data success proportion. So therefore, for the whole data as well, this gives us a lift factor. We calculate lift factor for different sample size to get lift charts. This is a sample lift chart. As you can see, on the x-axis we have our sample size in the form of percent of the whole data, and on the y-axis we have our number of respondents. As you can see in the lift chart, we'll try to stay towards the upper left corner. If we come back to the previous case, so we'll like to stay over here. That is, for the minimum sample size, we have the maximum number of respondents. The diagonal line is the curve for random sample without using sorted data. Any good selection will keep the lift curve above the diagonal. So this is the favorable area for a lift chart to exist for any learning method. Now we come to next visualization technique, which is ROC curves. These stands for receiver operating characteristics. They are very similar to lift chart, the only difference being that the y-axis shows percentage of true positive, and the x-axis shows percentage of false positive in samples. Now ROC is a jagged curve. It can be smoothened out by using cross validation. This is a sample ROC curve. As you can see, it's pretty jagged, but if we use cross validation, then we can smoothen it out. And as you can see, on the y-axis we have our true positive percentage, and on the x-axis we have our false positive percentage. Now we will look at ways to generate our ROC curve or our cost curve. Get the probability distribution over different folds of data. Sort the data in decreasing order of probability of yes classes. Select a point on x-axis, and for that number of no's, get the number of yes for each probability distribution. Now average the number of yes from all the folds and plot it. So this is our first way of plotting ROC curves. And the second way is get the probability distribution over different folds of data. Now sort the data in decreasing order of the probability of yes class like we did in the previous case. Now select a point on x-axis, and for that number of no, get the number of yes for each probability distribution. Plot a ROC individually for each fold, and in the end average all the ROCs. So the only difference is where we are doing the averaging. Now basically this diagram shows ROC curves for two schemes. If we are lying in this particular area, then we'll be using technique A. If we are lying in this particular area, if our false positive percentage is 60% or more, then we'll be preferring B, and in between we'll be using a combination of A and B with appropriate probabilities. Now we come to recall precision curve. In case of a search query, so basically recall precision curves are used when we talk of search queries. Recall is defined as number of documents retrieved that are relevant divided by total number of documents that are relevant, and precision is defined as number of documents retrieved that are relevant divided by total number of documents that are retrieved. So these are just formulas. Now this is the summary of all the three different measures which we use to evaluate the false positive versus the false negative trade-off. We talked of left chart, ROC curves, and in the end we talked of recall precision curves. Now we come to the next visualization technique, next type of chart, that is cost curves. Now cost curve plot expected cost directly. Example, for case with uniform cost, that is when our cost is basically our error matrix only, we can have the following cost curve. So this is basically we have two classes, plus and minus. On the x-axis we are basically plotting our probability of plus class, and on the y-axis we have our expected error. So if we take this dash line, this is the case when we are predicting we are always predicting the wrong answer, and if we consider the x-axis, this will be the case when we always are predicting the right answer. And similarly these two diagonal, this diagonal represent always, then we always pick negative, and this particular diagonal will represent that we always pick positive. Now for a classification A, we have the following line, and if we take at probability p plus equal to 0, we get FP, that is the false positive, and when we the intercept at probability p plus equal to 1, we get our false negative. Again, this is one more example. Now instead of error, we are using normalized expected cost over for the y-axis, and for probability cost function as our x-axis. Now basically how do we define these two parameters, probability cost function and normalized expected cost? Here are the formulas. In these formulas, C plus minus is basically the cost of predicting plus when the instance is actually minus, and similarly C minus plus is the cost of predicting minus when the instances are actually plus. And these are the formula, and using these formula we can find any point in our cost curve. Now we come to the last part of the session, that is minimum description length principle. The description length is defined as space required to describe a theory plus space required to describe the theory's mistake. Now in our case, theory is basically the classifier and mistakes are the error on the training set. So we try to minimize the description length. Now minimum description length theory is one that compresses the data the most. That is, to compress a data set, we generate a model and then store the model and its mistake. Model again is our classifier, and by mistakes we mean the error on the training set. So what do we need to compute? we need to compute the size of the model, and then space needed to encode the error. The second one is easy. We can easily compute the space needed to encode the error by using information loss function, which we started earlier. For the first part, we need a method to encode the model. Uh, if we use the following representation, LT equals to the length of the theory, and LE by T is basically the training set encoded with respect to the theory, then LT plus LET is basically our description length which we are looking for. Now we talk of a practical implementation of minimum description length. So we talk of minimum description length and clustering. The description length of this theory is basically the bits needed to encode the cluster. Now how can we basically represent a cluster? We can represent a clusters in the by if we mention our cluster centers, and description length of the data given the theory is encode cluster membership and possession relative to the cluster. That is, if we just give the distances to the cluster center. This is only useful if coding schemes use less code space for small numbers than for large number. So basically, by using the step 1 and step 2, we have converted large number to small number, and it will be only useful if the coding scheme gives us some advantage for using small numbers. So in this session, we talked a lot about how can we compare different data mining algorithms, how we can rate their successes and their failures. We also talked of a widely used technique called minimum description length towards the end. We talked of how we can incorporate cost during either learning process or during the error estimation process. And this brings us to the end of the session. Thank you.